Today is April 5th, 2017, and today I would like to cover the definition of a strain in terms of displacement vectors, and we will also study about the strain transformation, which is will be the same result as the stress transformation. And this slide has been updated from previous one, so please download this new version. Not much change, but I made a little change so that the old expression looks better. Okay. Well, last week we briefly introduced what kind of strain component we can have in two-dimensional case. Simply, I will use next slide. Simply, we have a three component in extraction and extension and y direction extension and angle change. But now, today, we would like to use the mathematical expressions for the normal strain, which indicate extension, and shear strain, which indicate angle change. Okay, let's consider rectangular with corner 0, C, D, E. The coordinate of point O is XY, and the length of in X dimensional is the dx, very small small length dx, and Y direction. We have a small length dy, and then now this rectangular would deform, and each corner will have a different coordinate, and the 0 will move to O prime, and now the displacement at X and Y, and the displacement here, let's call X directional displacement and Y directional displacement. Now the C point, now we have a displacement UX. Now this UX and UI would have additional terms because this one is going to extraction, so there will be an increment partial difference at UX, round UX, round X, and DX. These terms will be additional terms. And also Y, this is second term, Y would also have an additional term in extraction, round Y over round X and DX. That is the a new coordinate of this point C. So C prime will have this and that, and notice that there is the X directional increment because we moved from here to there. So C is a point with a dx in extraction. Now this ux and uy, and there's another point. E will move to E prime, and let's indicate the displacement in terms of different infinitesimal displacement. UX and UI, again, same as before, UX and UI. Now we change it in Y direction. So this term, this displacement will have a x direction. There will be a y increment and uy also a y increment. And so this one will have a new coordinate of e called e prime, and you can compare this c prime and new coordinate. Looks similar, but the difference is here is the x directional differentiations, and here is a y directional differentiation. So so this is a displacement field, and of OC, DE, and O prime, C prime, and D prime, E prime. We didn't consider D prime and from D to D prime because all displacement will be uniform, and so D is a dependent. Now, let's try to define the strain field using this displacement. Same figures. Now, by definition of the X strain, okay, this is important, X strain, the original length was the dx, that is the X directional original length, and then this new length, this X directional new length, okay, this much new length will be this much minus ux. This will be an x directional extension. So strain is simply L over delta. Delta is increment deformation. So x direction is simply dx, and y direction elongation is simply this term is that one, and minus ux, because it has to be a relative displacement, and there will be minus ux and divided by dx. Well, simply this ux disappear, and then I'm sorry, this has to be x and x, okay? This is x and x. And now simply this dx and dx disappear. Okay, so this is the final, very simple form. In displacement field, ux, uy, this is a displacement field, and strain in x directional length change is that simply ux derivative with respect to x. Similarly, we can obtain the y directional strain is again the length elongation in y direction with respect to a y directional length, dy, and again similar to epsilon xx, we have a y and y, and we can easily get the uy derivative with respect to y. That's the strain in y direction. Now, one of the most important strain is the shear strain, which is the change of angle. Here, the change of angle is original configurations, and there was a rectangular, and now we deform as the O prime, C prime, D prime, E prime. The angle changes this one, and angle changes that one. So by definition, we define the strain as this one of E O C. This is the and this is the original angle, and now we have a new angle this much. Okay, this much, which is the E prime and O prime and OC prime. So this is the original angle, well, which is the simply pi over 2, right angle, and then this angle. And so simply the theta 1 plus theta 2, this one and this one, this, and plus and average. So we, by definition, we average of those two angle difference. Now, very importantly, what is the theta 1? Well, theta 1, you can see that approximately this and that tangent theta 1 is simply theta 1. What is a tangent theta 1? Tangent theta 1 is that this vertical displacement, which is the y directional difference. So that is the y directions, and this divided by the dx will be simply y derivative dx. That is the this term, and divided by dx, and simply uy divided by dx. Okay. Now, what is a theta 2? Well, similarly, we have a tangent theta 2 is approximate to theta 2, and theta 2 is say this one y directional component. Sorry, this one is x directional displacement divided by dy, and this one minus x will be simply ux y and dy divided by dx, and so this one and this one disappear, and this one was it disappeared as well. So this is the final form. Okay, so this one epsilon xy by definition, or the same as epsilon yx is the same by definition. They are the same, and pay attention here. Y directional displacement, derivative with respect to x. Now, x directional displacement, derivative with respect to y, and help. Okay, so this is the three strain component, actually 4 component. Now we can use these index notations, and epsilon xy and epsilon yx, they are the same. And index notation means that one index notation will indicate this and that, all three. So we can use index equation like that. And here, if I equal j equal x, let's see what happens. Xx and x and x and x and x, so that will be these terms. And what if I equal j equal y, then y, well, that will be the epsilon yy. Now I equal x and j equal y, or vice versa, then epsilon xy will be half of epsilon ux y and x, which will cover this one. So it's good to know to use this one index notation, which will cover these 4 strain components. Okay, that's the definition of a strain. In terms of displacement vectors, now, more importantly, we need to understand the meaning of the strain, and now we will transform the strain field from one coordinate to another coordinate. So what is the strain transformation of strain or strain transformation? Simply, we have some sort of a deformation field in XY. XY means we are looking at the strain field using XY coordinate. Okay. Now, that is the strain component. Now we are looking at the same, okay, same strain field, but we are looking at the strain with a different coordinate, which has some angle difference, angle rotations. And coordinate transformation from one axis to the other axis, we do know there is a simple transformation rules. But here, what we would like to do is that to drive transformation rule from one coordinate to another coordinate. Very similar concept to a stress field, stress transformation. The way we drive the strain transformation is to use the definitions, epsilon x prime. Now, by definition, this will be x prime and x prime. And this x prime and x prime, now x prime has the, we can differentiate using chain rule. So you have a x and y. And as you can see here, we have x, and here you have x and x and x and x. This is simply a chain rule. Now here, the stress coordinate transformation from this is simply cosine. This is a cosine theta, and this one is simply sine theta, which can be obtained from these relations. We can copy this one into here for reference. Okay, so x derivative with respect to x prime, that this term will be x with respect to x prime will be a cosine theta. That is the cosine theta. And y with respect to x prime, y prime, x prime will be a sine theta. So this will be the sine theta. Now, how about these terms? Well, this term is now this term simply ux prime, okay, ux prime equal and uy prime, that also follow the coordinate transform because they are simply vector. So cosine theta and sine theta and minus theta and cosine theta and ux, uy. So ux prime derivative, with respect to x, is that cosine theta ux, x comes from here, and also ux prime, there's a second term, sine theta and uy, sine theta and uy, and there's x. We can do the same for these terms. well, looks a little complicated, but it's very much consistent. And this is the this term. And we use x prime with respect to y, okay, with respect to y. Okay, so this should be y. And cosine and sine theta. Now we combine them, and combine, we can see that I'm going to use a different color. It's a little complicated, but as you can see here, the cosine theta and cosine theta, we have a cosine square. And there is a sine theta, and the sine theta, we have a sine theta. Square. And also we can have a sine theta and cosine theta. We have a cosine theta and sine theta. We have this term. So we this is the a strain transformation. And please notice that what is this term? Well, this is the, by definition, it is epsilon xx, and this one is the epsilon yy, and this one is the twice of epsilon xy. And others, like a cosine square, comes here, sine square is here, and this one. So this is the strain transformation, epsilon x prime, in terms of previous coordinate, component. And you can notice that this form is exactly same as the stress transformation. You know, you can easily remind that sigma x prime equal sigma xx cosine square, sigma yy sine square, and 2 times of a sigma xy, and so on. So this is, we can easily notice that this is exactly same as a stress transformation. We can do the same for the epsilon yy, and this is the final equations, and epsilon xx, yy, and xy. Notice that we have a sine square, and while here is cosine square. Well, also, we can transform epsilon x prime y prime from definition is like that, and do the similar procedure as above. Now we have this term and this term. And again, we can see that these 3 strain transformations, 3 component is exactly same as the stress transformations. Very interestingly, the physical meaning of the stresses are totally different from physical meaning of strains, but simply their transformations are the same. Well, mathematically, there is a clear reason for that. Simply, they are same order of a tensor, second order tensor. So sigma ij and strain ij are same as the second order tensor. Well, what is a tensor? Well, it would take some time to explain about the tensor. First, the second, third, and so on, higher order tensors. If we, they follow, the conclusion is that as long as they are same order of tensor, their transformation rule are the same as like in stress and strain. Okay, well, again, these are all mathematical expressions, but we need to clearly understand what it means, strain transformation. Okay, I I made a new slide, which will, I hope, help us to understand better the meaning of the strain transformation. Okay, strain transformation in two-dimensional case, the meaning of a strain transformation, first we observed the same strain field using two different coordinates. What does it mean? This is the before deformation. Before deformation, we just mark. You just mark like that, and mark like that. But notice that this is the same material and the same, exactly same one. Now we apply a strain in extractions, only extractional strain, and you can notice that this original, this rectangular in XY coordinate would expand in extractions. Only in extractions. Epsilon XX is only, for example, in terms of a magnitude, it has a non-zero. Others will be zero. Notice that epsilon YY is simply zero. Well, again, they are exactly same material and same deformation, which means the same strain field, but we observed this same strain field in different coordinate. What do you mean by different coordinate? Is that we draw a rectangular like this coordinate system, x prime and y prime, and the same strain field, but you can see that this rectangular would deform in different format, different form, like x prime, we can see that this angle or this angle has changed. So certainly they are the same strain field, but there are, you can see that epsilon YY and epsilon XY now in x prime, y prime, epsilon x prime, and epsilon y prime, and epsilon x prime, y prime, they are simply different. How to obtain from here to there? That is the definition of a strain transformation. So it's important to keep in mind that we are looking at the same strain field, but the components are with respect to a different coordinate system. The same strain field, I will repeat it here, have a different strain component in different coordinates. So what we would like to drive is to transform or change it from this three component to that component. That is what we have observed, what we have obtained in these procedures. Okay, that's the meaning of strain transformations. And since the mathematically exactly same as the stresses, we can use Mohr circle using the same, similar to a stress, we can easily obtain this transform the strain component in terms of 2 times of theta, not just the theta, 2 times of theta, and then we can draw same circle as a stress. Now, as we notice in the stress transformation, this is the center of this coordinate. Okay, this coordinate I will call just C. Okay, so this is the coordinate. Now we have 2 terms, this minus. Okay, if we look at this angle, I mean the triangle, and this one, what is this? Well, this one is the epsilon x minus epsilon yy divided by 2. So that is this term. Now there we notice that multiply cosine 2 times of theta and epsilon xy. What is the epsilon xy? Epsilon xy is here. So this is the epsilon xy, and this much is the epsilon xx minus epsilon yy divided by 2. So and there is a cosine twice of theta and sine twice of theta. So here, let's say we transform from, we used to call this one is x, right? And we used to call this one is the y. I will write here, strain can be epsilon xx and epsilon xy and epsilon yy and epsilon yx. And now we call x as a these terms, and y has this term. And this x-axis indicate the normal strain, and y indicate epsilon xy. But epsilon xy, we need to be careful, as we noticed in stress transformation. Epsilon xy is a positive for x, and epsilon positive for the y. Okay, we need to be careful. What it means is that epsilon xy is the positive, then if the point will be located in lower region, and if this one is the positive, then y will locate the upper region. Okay, so this is the Mohr circle, and we also notice that this one and this one, that is simply the new shear strain. So drawing Mohr circle, the drawing procedure of Mohr circle is exactly the same as the stress. First, we simply draw this one, okay, x, locate this x, that's number one, first step, and draw this y, this is number 2, and then make a circles with x and y as a diameter, and draw circle, simply draw circle. And so draw circle will be a third step, and then rotate by 2 theta, okay, rotate by 2 times of theta, and so this one will be, we call x prime, and that will we call y, y prime. So you can just read the coordinate of this point and coordinate of that point. That is the Mohr circle. Well, we already have the Excel, which we derived from stress transformation. I simplified, but as you can see that it has equations. This term, sigma xx plus yy and minus, and that's a cosine and sine, and sigma xy. This is the formula, and this is the angle theta, and we simply plot, as you can see here, we click and you can see it graph shows in terms of theta. And here, radius. Now, I additionally draw a Mohr circle. Mohr circle, all you need to do is just, because this is the sigma xx and that is a sigma xy, you simply select this this column and that column and draw. I will simply show you one more time. Just select 2 columns and insert, and there is the plot chart, and do that. and then make the same length. This is a 3, and that is a 3, and this is a Mohr circle, and this is this one. Okay, and now radius is simply our the center is over here, and radius is there, and sigma simply the center and radius, it can be easily calculated, and sigma P1 means that principal stress there, and sigma principal 2 is there. Please, you can also download this Excel file, and there's a shear maximum which is the same as the radius. Now you can enter this value, say 1, 0, 0, and you can see that this is a 1, this is the x, and that is a y, and you can draw, and this is a Mohr circle, and radius and centers. Again, you can enter any value, and you can notice, the Mohr circle is directly obtained from plotting this and that. And you can see what will be the maximum shear stress and what will be the principal stress. And you can observe many things from this Excel plot. So very useful tools. So I will save it, and you can download it. Okay, so that's what I would like to cover today, and hopefully you understand what we have done, what we have studied is that first we define the strain in terms of displacement, and then we derived strain transformation using coordinate and vector transformation. Is just use the chain rule, and we come to this conclusion, and epsilon x, y, xy, and this we can notice that that strain transformation is exactly same as a stress, and this is the important drawing and the meaning of a strain transformation, and we are able to draw the strain and Mohr circle for the strain field. Sometimes some textbook define epsilon xy as twice of epsilon xy we define as the gamma shear strain. So that often define like that, and certainly twice of epsilon xy prime will be a gamma prime. So please don't be confused by this. This is called engineering shear strain. Gamma, okay, and epsilon xy is the just simple mathematical tensor strain. That could be the only one difference depending on the definition. Other than that, strain and stress transformation is exactly the same. Okay, that's what I would like to cover today, and thank you. If you have any question, please send me email or ask me tomorrow. Thank you.